submit tonight or maybe sometime tomorrow if you want to prefer to send me email on this. And we do have new homework assignment and computer assignment, which are mainly related to unconstrained and constrained optimization problem. And the material that I'm going to talk about tonight actually is not the main focus in the textbook, so I will not probably have new homework assignment for you on this subject, but indeed it is a very important topic to study in the optimization, especially when you have discrete decision variables. So I will try to provide as much detail as I can in terms of the examples. And also, no, I cannot change them. Okay, so dynamic programming, you can think about this. It's just like a technique for solving certain type of discrete optimization problem. And here, discrete means, well, not continuous, means the decision variable takes discrete values or something not exactly. You can say the decision actually takes multiple stages as well. And that's very special in terms of the optimization problem. And the idea, of course, is to break a large, complex optimization problem into many smaller, much easier ones, so that the computational requirement will be reduced. In order to achieve that, usually this technique can only be applicable to problems where a sequence of decisions over time have to be made in order to optimize certain like long time horizon criteria that involve is like a multiple time step decision overall. And this has a lot of engineering applications in decision or maybe some other planning problems where solving the problem involves multiple stages. And of course, for discrete optimization problem, you can always try to search or enumerate all the possible solutions and find the best one. And like what we explained last time, such a problem, in general, by doing enumeration is not computationally efficient, and the problem doesn't scale very well. So in some real engineering problems, solving such a problem optimally by so-called dynamic programming technique is very useful because you can prove that this technique is computationally efficient and also doesn't lose any optimality. Like last time, we also talked about some algorithms may be efficient, but there's no guarantee that you can find the optimal solution for discrete optimization problem. And dynamic programming is a nice mathematical technique that you can prove it does provide you the optimal solution. And it is much more efficient than enumerate all the possible feasible solutions in the discrete set. So you can think about the problem that involve multiple stages in the decision, like, for instance, find the shortest path in some directional acyclic network where you have a source and a destination. And you have many possible routes to consider, and the art of doing dynamic programming lies in how to really construct some specific network where you can control the expansion of your intermediate state, where you need to only keep a finite set of states in order to maintain the optimality in the decision. So let's start with some example on the so-called shortest path problem. I think maybe some of you already encountered this problem before. I have some feeling about what it is, and some may not be that familiar, but bear in mind, this is a very illustrating example that when you understand how we solve the problem for this shortest path problem, then you will understand better in general how to solve dynamic programming problem. And let's assume that you're currently living in New York City and plan to move to Los Angeles. And you will drive. And to save money, let's assume that you will spend each night of your trip at your friend's house. And I'm sorry? Okay. And just to make it convenient, you can assume that you have some potential stopovers at different places in this road trip. On day one, you can reach Columbus, Ohio, Nashville, Tennessee, or Louisville, Kentucky. As the second day, you can reach Kansas City, Omaha, or Dallas. A third day, you can reach San Antonio or Denver. And eventually, you plan to reach Los Angeles on the fourth day. Okay, so the question is, for instance, which plan would be better? Like maybe in terms of the mileage, in terms of other considerations that we are going to optimize. And in this particular case, if we say shortest path problem, that means we try to save the mileage in this drive. Okay, so to minimize your gas expenses, of course, you are looking for some itinerary with the minimum length. How are you going to determine your itinerary in this case? Well, if you think about the problem in this kind of setup involves multiple stages of decisions, right? And that's exactly what we are looking for. And you can classify those different cities into the different categories. You can say all those cities that you can reach at the beginning of your end state is called stage n cities. For instance, you can say stage 1 cities will be what? Like the first day you can get to that. And stage 2 city, you can say from stage 1 then to the next one where you can get. And then, of course, the idea of solving this problem by dynamic programming is to what? Explore all the possible cities. You can, of course, you can always enumerate all the possible stage-wise cities and then try to pick the shortest path. But that's not efficient. And the idea is to solve a relatively easier problem first, and eventually you will solve the more difficult one by these multiple stages. And if you think about the problem, you can go forward or what? Backward, right? For instance, if you think about you're going to Los Angeles, right? And then what? You can go backward saying, in order to reach Los Angeles, what would be my previous stop, the city that I have to stay, for instance? In that case, you can think about the distance from a particular city I to city J, which is the cost that we call CI to J. And in this case, you can go what? You can go multiple stages, but if city I is a stage T city, and then, of course, we can denote the length of the shortest path from city I to LA by some cost. And that involves this stage T. Okay, so that means this is a stage T city to Los Angeles. Okay, and why we need such a notation? Because we can decompose the city into different stages because we can plan ahead of time. So we would like to find from New York City, that's like the starting point, we want to get to Los Angeles, right? Okay, and now how can we view this shortest path problem into different stages? At the very beginning, you may want to find the shortest path to Los Angeles from each of the cities where you can reach in one day, which means we are looking into what? Just in 4 days, we are looking into stage 4 cities, right? And then what? Then we want to say which city is closest to LA, right? And that's where we probably want to keep an eye on. So in this case, this problem is trivial since, for instance, in our setup, you can say there's only one way to get to Los Angeles in our itinerary. And formally, you can say there's only one city that you can get to Los Angeles, which is what? I hope that I can easily get to the problem first so that you can record this, which I hope that maybe I should make a note on the document camera that need a darker one. So 1 is what? New York City, right? And then 10 is what? Los Angeles. And then stage 4, stage 3, stage 2, stage 1, stage 0, right? And stage 4 means what? On day 4, you reach to Los Angeles. On day 3, you have what? On day 3, you have 8, 9, right? On day 2, you have 5, 6, 7. 5, 6, 7. On day 1, you will have what? 2, 3, 4. Can you remember what are these cities? Well, I hope I will just put some note here. This is San Antonio, and this is Denver. And then 5 is Kansas City, and then this is Omaha, okay, and then this is Dallas. Okay, and then 2 is Columbus. This is Nashville, and then Louisville. Okay, so now at least you have something to record on. And from this, let me directly switch to the slides I'm looking into. So if you think about how we are going to work on the shortest path, we can go forward and enumerate all the possible routes, or we can go backward, just record where's the shortest one to get to LA, and then what? And then you can basically see how you get to the next stage from the minimum one first. So basically you can find the shortest path to Los Angeles from each of the cities from which you can reach to reach LA in one day. This is like the stage 4 city. And this problem, of course, is trivial. And next, you're going to what? Find the shortest path to LA from each of the stage 3 cities. And in this case, you should first get to a stage 4 city, right? And then what? use the shortest path from this stage, from this stage 4 city to Los Angeles. And of course, this problem is in general not a trivial problem as the first one. But you could still simply enumerate or exhaustively search all possible city 4 problems, and then the solutions to the first set of the problem remains relatively easy. And what? From each stage 3 city to go to a stage 4 city, then you use the shortest path from this stage 4 city to the LA. And for example, if you stage 3 city, which is what? Number 5, you need number 8 and what? You can go 8 or 9. And we are interested in what? Which one is shorter? Right? So we have the previous cost and the cost to go there. Make sense? So if you get to this, if you think about, I can go from here to here or here, right? And then what? I'm looking into what? This city from Kansas City. Which way should I go? Which way is better? I can go this or this, right? These are two possibilities from Kansas City to LA. Which way should I go? The shorter one, right? So there are only these two choices I can make. And then I just keep one of these, right? And what about 6? Almost the same thing. It's like this and this, right? So you can always think about, this is what? The initial cost to get to there. And then this is the cost to go. So you can always decompose the problem into what? This is intermediate state, right? 8 and 9. And then you just basically compare what? This is the total cost, is the initial cost, and then the cost to go. And then you just try to keep whatever is the minimal. And that's not like enumerate all the possible routes. This only depends on how many states in your previous stage. Not like you enumerate all the possible combination of the routes. Okay, so if you think about this problem, you can perform what? In many, many different stages, right? In this case, we have like a 4-day trip. And intermediate states is not very large. But let's say if you have 10-day trip, then you have many different combinations to look into in your plan. And still, you can do stage by stage. If you do enumeration, which is not as efficient as what you do here. So you can perform this until you reach stage 1, which is New York City to begin with. And then what? And then the minimum route that you get is, in fact, the shortest path. You should travel from New York City to Los Angeles. So in this case, you can say from New York City, you should first go to a stage 2 city and then use the shortest path from stage 2 city to LA. And in general, this is true for any stage because the shortest paths have to include that portion where you already find the minimum up to that point. Any questions? Okay, so in this case, once you reach stage 1, then you basically find the best route from New York City to Los Angeles. And also, you already considered all possible stage 2 cities. So in general, you can say at any stage t, we are interested in finding what? The cost from the initial stage up to that point. And that can be decomposed into what? The cost get into the previous stage, and then the cost to go from there to your current stage. So using this notation, you can think about at stage t, we need what? The cost from stage t plus 1, and then what? The cost, additional cost to go from that city to your current city. And this will involve with how many states in this minimal. That depends on like how many cities you have to consider in the previous stage during your plan, okay? And this is the key structure of dynamic programming. And in this example, of course, we could simply enumerate all the possible routes from New York City to Los Angeles. And if you want to think about the complexity of this calculation, you can see that because we are talking about what? 3 stage 1 cities, 3 stage 2 cities, 2 stage 3 cities, right? So we are looking at like what? 18 possible routes to explore in this case. However, let's assume that if we have more options to explore, let's say if you have 5 cities in stage 1, and then maybe let's say if you have 5 stages in each city, and then let's say if the destination is at stage 7, then to simply put, if you have 5 cities in each stage, and then you have 5 stages to explore, then you have 5 to the power 5 possible parses you need to explore. And to determine the minimal length for all these parses, you need about 15,000 total additions and maybe over 3,000 comparisons on this. So I shouldn't go that fast, I guess. Okay, so if you think about by doing dynamic programming, we are not really trying to enumerate all the possible parses, but in general, each stage, what do we need? If we have 5 cities, then basically we say the state space is only 5. And then we will need 5 additions and possibly 4 comparisons. And the overall computational cost is what? Not exponential in terms of the number of stages. It's what? Just the product of all the stages we need, in this case, is only about around 100 additions and maybe 84 comparisons in order to get to the optimal solution. Okay, so to recap what dynamic programming technique is applicable to some problem, which we have to see the problem can be decomposed into stages. And each stage corresponds to a point at which you need to make a decision. So each stage should have a number of associated states. And that usually is discrete in nature. Of course, later, if we have time, we can also explore so-called dynamic programming in continuous space, and even stochastic programming, where the objective function may not be deterministic. It may have random perturbations due to noise or due to your inaccurate observation of some hidden state. But first, let's think about that in the shortest path problem, the state contains actually all the information that is needed to make an optimal decision for the remaining problem. What do we mean by that? If you look at the shortest path problem, okay, so we are looking into any particular city at stage 2, let's assume. At stage 2, we pick a city like Kansas City, okay? And then what? In fact, we are looking into what? All the possible ways to get to Kansas City from LA, right? Right? And then that basically will involve is what? Only stage 3 cities, right? And stage 3 city encapsulate that. Do you agree? And that means you don't lose anything if you say, I can guarantee that the cost to get from LA to San Antonio is the minimum, right? And then if you can guarantee that, then I can guarantee you the way I calculate the cost from LA to Kansas City is still minimal, right? If you can guarantee for stage 3 cities, San Antonio and Denver, the cost to get to there from LA is the minimum distance, then I can guarantee you my calculation to stage 2 cities are also minimal. Can you see that? Yes? Okay, and that's important for dynamic programming algorithm to work. And sometimes, if this assumption is not valid, then we have some problem. Okay, and the decision that we choose at each stage actually describes how the state at the current stage is transformed in the state from at the next stage. And this next or previous or whatever is just for the sake of convenience. Why do I say that? For instance, can I work from New York City and do the same calculation? For shortest path, can I? Can I work not from Los Angeles, but I want to work from New York City to do dynamic programming? Can I do that?
Yes.
Yes. How? I will say from New York City, what? I will go to what? 2, 3, and 4, right? For stage 1, I will record what? The minimum cost to this, right? Which is just the distance. And then what? For the same thing, for Kansas City, what do I need to do? I need to compare what? These 3 distances and then find what? The minimum, which is what? The minimum distance from New York City to Kansas City from 1 to 5, right? Because I need to go through 125, 135, or 145. And same thing for Omaha, for city number 6. I can also do 126, 136, and 146, right? And then basically I can go from New York City to Los Angeles working on the other direction. Why? Because the cost is just the minimum distance, doesn't really say the beginning or the end. You measure the distance, right? And that means you can, in fact, start from anywhere. If you have a so-called directed acyclic graph in this kind of road network, you can compute, you can pick any 2 cities and then try to find the shortest path. And we will get into that shortly. And that's important for you to understand how the dynamic programming works. the optimal decision at the current state should not depend on the previously visited states or the previous decisions. Can you see that? For instance, in the shortest path problem, if I go from New York City to Columbus, the distance is fixed, right? And it doesn't really matter later I go to Kansas City because I have to go from New York City to Columbus and then to Kansas City. On the other hand, in some other decision problems, there might be the cases where how you choose your current state depends on your previously visited states or your previous decision. Can you give me some example? So is there anybody playing chess? Or checker, or Go, or whatever game you can think of. And then you can think about, that's a sequential decision problem, right? If you play chess, then your previous move, your opponent's previous move definitely will affect how you respond. And then your future move, of course, will depend on a consequence of that. And what? Then you cannot decompose the problem into multiple stages where each stage you only consider what? Like the cost that you get to the previous stage and then the cost to go from your previous stage to here. You cannot do that, then you cannot use dynamic programming. So the most important assumption that we have to make in this case is called the principle of optimality, is that the optimal decision at the current state doesn't really depend on your previously visited states or the previous decisions. And that's the key for the dynamic programming algorithm to work. And in general, the algorithm works in some recursive way. You can say you relate your final stage into your previous one so that you can say if there are capital T stages, then you go from T plus 1 up to capital T so that the cost or reward can be related by what? By some mathematical description linking between the previous stage to the current stage through the inherent internal variables. And this recursion formalizes the procedure of working either forward or backward. And in many problems, actually it works backward because usually you know the final goal. And then you try to go backwards to retrace to what would be your initial decision. However, working forward usually is considered computationally expensive because you got to enumerate all the possible branches in your next stage. And that's basically the idea of dynamic programming. And for the shortest path problem, we can make it in a more formal way so that you see how dynamic programming solves this problem and maybe even solves other more generic problems than just the shortest path problem. And there are 5 stages, and in this case, the inherent state is what? Just the city that you're going to visit. And the decision is what? At each stage, which city you pick. So dynamic programming recursion, you can think about, from the last stage, you get to what? A minimal problem where what? J is any city in stage T plus 1, then at stage T, you need what? The cost or the distance to travel from Los Angeles to a T plus 1 city. And then what? The distance from that city J to what? To your stage 4 city I. And then basically, you do a recursion. You can go backward from 4, 3, 2, 1, and then whenever you reach the beginning city, you're done with that. Okay, so this is actually very nice structure. And of course, if you think carefully, this may be applicable to more general engineering problems where multiple stages are involved. However, for shortest distance problem, in fact, these stages doesn't really matter too much. Oh, does it? Well, maybe let's consider just a road network where you want to pick something like shortest distance from the road network. Do you have to consider stages at all? Let's say if you must drive from Bloomington to Cleveland, and you are interested in the route that takes the least amount of time, let's say just equivalent to shortest distance, without considering too much about traffic load, road condition, and other issues. Okay, and let's say this is Bloomington and that's Cleveland. And this is a simplified road network where you have some possible cities you may want to encounter. Okay, and then let's say from Bloomington to Indianapolis, you have 1 hour drive, and from Indianapolis to Dayton, you have 3-hour drive, and so on and so forth. So you could go, for instance, from Bloomington to Cincinnati, and then to Columbus, then to Cleveland. Or you can go from Bloomington to Indianapolis, to Gary, to Toledo, and then to Cleveland. You have different ways to go. Do we really, in order to find the shortest paths, do we really need to enumerate all the possible routes? That's the first question. And second question, do we need to decompose the problem into multiple stages? If yes, how do you do that? If no, what do you want to do? Any idea? I'm sorry?
You don't need to enumerate all the patterns.
Okay, so what do you want to do?
For example, first from Wilmington, you can go to the Minneapolis first. It's 1 hour.
You get to where?
And to Minneapolis.
Indianapolis.
In Indianapolis.
Okay.
Then try to find the second shortest path from Indianapolis to Gray. Then the total hour is 3.
Okay.
Then it's the same as the 3 hours to Cincinnati from Bloomington to Cincinnati.
Okay, but then you are actually enumerating, right? Or not? Or not?
Really. At this stage, she's choosing the best option at that stage.
Okay, so you're saying that each city you just find pick the best one. Okay. And then what?
But that's greedy.
That's greedy. Would that work, basically?
That may not lead to an optimal solution.
That may not lead to optimal solution. But is there any way you can find the optimal solution?
Yes.
How?
You use dynamic programming.
Okay, but how do you do that?
You start in Cleveland, and you see the Toledo.
Well, in order for dynamic programming to work, we need to make sure what? 2 conditions.
You can decompose it into that.
Okay.
And wherever you are, getting to the end.
You can decompose this in the overall goal into multiple stages. That we can, right?
Yes.
And then what? At each stage, your decision only depends on what? Like the cost to get there from your previous stage, right? So now we have to first think about, do we need to decompose that into multiple stages? I think we do, right? And then how do we do that? Here, how do you declare stage 1 city, stage 2 city, so on and so forth. You can say Cleveland is what? Stage
0 or final.
Stage 1, let's say stage 0, okay? And what are the stage 1 cities? Okay, Toledo and Columbus. Okay, and what are the stage 2 cities? Gary, Dayton, and Cincinnati. And what are stage? We have like 1, 2, and then 3. Stage 3 cities are what? Indianapolis and Bloomington. Now what? What do we do? Do we need stage 4 city? Okay, that means given stage 3 is Indianapolis, we have stage 4, right? Yes. Otherwise, what? Given it's Cincinnati, then what? We don't have that. But we have stage 3 cities already, Bloomington. Agreed? Yes? And then what? Then you already know what we did before, right? Then if you say, well, I have one problem that Bloomington is stage 3 city and another sub-problem where it is stage 4 city, then what do? You apply dynamic programming, what? On each cases, and then compare which one is better. Right? Yes? Is it better than enumeration? I would believe so. Is there any way you can avoid doing that? Avoid using multiple stages. Like we still now say Cleveland is stage 1, right? And then in that case, Toledo, Columbus will be stage 2, right? And then we say Dayton, Gary, and Cincinnati will be stage 3. And Indianapolis and Bloomington will be stage 4, so on and so forth, right? But my question is, for instance, is it possible that a city could be multiple stages? Yes, right? Can we avoid enumerating all those possible stages?
You just use the cities themselves as like nodes and find the minimum distance from that node to your goal.
I'm sorry?
You find the minimum distance from any node to the goal. You just
okay.
Concept of stages altogether.
Okay.
Same algorithm. You just have to keep track of who is neighboring who. Who can, like which nodes are neighbors of which other nodes.
Okay.
In terms of the direction and travel.
Would that work?
Yes.
And what about other students? Do you think they are following your thoughts, or maybe they're thinking about a different idea on this?
Can't explain myself very
well. Well, let's try one more time. I think we agreed that in order to find the optimal route, optimal path from Bloomington to Cleveland, we are going to calculate stage 1, stage 2, stage 3 cities, right? And then put a table and then what? Apply dynamic programming to that. But now we see there's a potential that, for instance, Bloomington may become what? Either stage 4 city or maybe stage 5 city. And I think that can happen to any intermediate city like Dayton, Indianapolis, or whatever, right? And the question is, how are you going to reconcile that if a city may appear at many different stages? so that you have many different dynamical programming problems to work with. Because that could potentially be somehow equivalent of enumerating all the possible combinations of the routes if the stages also blow up in such a way. Is there any way we can control that? Yes?
Can we introduce an extra node into the graph?
Introduce what? Extra.
Like, say Bloomington goes to Bloomington prime and the transition between them is 0 hours.
Okay. Then how would that help in reducing the possible number of searches, number of comparisons among different routes? Well, still look at this graph. What's the difference if Bloomington is in, let's say, stage 4 city or stage 5 city? If it's in stage 4 city, which means virtually it has to go from Bloomington to Cincinnati to Columbus to Cleveland, right? And if it's a stage 5 city, that means what? It has 5 stops to get to Cleveland. And that means what? It got to pass Indianapolis. Of course, this may be just your intermediate step, right, in a more complicated road network. But we just settled that we have to consider what? Both cases and try to find which way is shorter, right? Right? Then what's the key in this kind of problem? Like what Sarah just mentioned, if you look at some small structure where, for instance, you have Dayton as the stage 2, and then you only have these 2 intermediate stage 1 cities, then what? Then basically you can claim from Cleveland to Dayton, you know what would be the shortest distance, right, involved. Then what? Then this structure basically is fixed. Then what? You can basically think about that's like you shrink these 4 nodes into like 2 nodes, into just 2 nodes. Whenever you go from Cleveland to Dayton, you need the minimum distance of this. You need 2 stages, right? There's no ambiguity at all. And then what? The graph can be significantly simplified from there. And then you can get to Cincinnati. And same thing for Indianapolis. However, the difficulty lies in what? For instance, if there's another alternative path directly go from Bloomington to Cleveland, let's say if there's an arrow from here to there, then what? Then you've got to keep that in your list. Do you agree? And same thing, if there's another alternative from Indianapolis directly to Cleveland, then you've got to keep that in your state. So that means even though this is still shortest path problem, whenever you have a graph where you have some kind of tree structure, then you can basically simplify that by putting this block together, so that will reduce the complexity. But whenever you have arrows that cross, there may be the grandparent to the child in this tree structure, then your complexity will increase, right? In order to maintain optimality in dynamic programming, then you need to keep different subproblems if they are in multiple stages. Make sense? So in this case, I would say dynamic programming is not directly applicable until you break the problem into specific structure. Okay, so let's look at another interesting engineering problem where we are talking about production and inventory planning. And we consider this planning problem just for producing one single item. And we plan for T periods with some assumptions that we assume the demand for the item in each of the period is known. The initial inventory level is also known. At the beginning of each period, you must decide how many units to produce, and the production capacity is, of course, limited. Each period's demand must be met on time, and there is a limited amount of storage space available so that if you produce more, maybe for the future demand, you can accommodate accordingly. The goal is to minimize the total production and the inventory cost over a long planning horizon, so that basically, if you know the demand ahead of time, you have a scheduling sequence to tell the factory, the manufacturer, how to do in a periodic review model. In this specific periodic review model. And this problem, an optimization problem, I would say yes, because it has well-defined objective function, and also it has this discrete decision in nature because you plan in T periods, and in each period, at each particular planning time, you need to know the demand. At period T, let's say dt is the demand. And then, of course, you need to have the associated cost for producing X units in this period T, which we call Ct of X. And sometimes, this function may be independent of your time, meaning that, for instance, if you just think about producing specific item, that doesn't depend on when you will produce that. Then it's just a function we call C of X. And at the end of the period T, the inventory level is I. Then there's a cost associated with that, which is usually some charge for that. And also usually the inventory cost doesn't depend on a particular time, only depends on how much you put into the inventory, like how many items you need to store in the space. So that could be just a function h of I, okay? And if the production and the inventory holding cost functions are linear, then basically we say this is a linear program. Why? Well, the objective is what? Minimize what? The total cost for your production and the inventory, right? And then the cost, this cost function, this C and H are linear function. And also what? More importantly, the constraints are also linear. So this is, in fact, a linear program. And that, do you know how to solve that? Well, maybe not to the level of detail, but at least you should say some commercial linear program solver using simplex or interior point method or whatever technique that usually scales well in terms of the decision variables you can handle for linear program. And if the production costs assume to have some structure with fixed charge plus something proportional to how much you produce, then basically it's like maybe some function c of x is 0 if x is 0. Otherwise, it's a plus bx. And why there's an a here associated with that, usually it's like when you try to put the machine into the operating mode, you need to have some additional costs for maintenance and for this, how should I put, for the depreciation of this machine. In that case, we can basically also formulate this problem as what we talked about last time. This is like mixed integer linear program. Why? Why it is called mixed linear integer programming?
The values of x are integers?
I'm sorry?
The values of x are integers?
Why?
Or producing items, units of something.
Okay, which means
it's a whole thing.
Yeah, you cannot decompose that into 0.5, 0.3, right, unit. You have to say, well, the inventory is also measured in terms of the each unit. So the decision variable at each stage is what? Integer value. It's either 0 or some positive integer. So that's integer programming, and why it's mixed linear integer programming. What about the objective function? Is it linear function? That's important. It is, right? And what about constraints? They are all linear constraints. But then the decision variable, it's, in this case, is integer, so we have to consider about that. And of course, if you think about the whole problem, in general, you can formulate it as nonlinear optimization problem. If the cost is a nonlinear function of how much you produce, then what? If you have nonlinear constraint on how at a different time you may have different requirement for the inventory, and also the costs are different, then you have to think about that's the most difficult situation you may encounter for the production and inventory costs. And sometimes you may assume that these costs are concave function of the product you're going to produce, and that's reflecting the economies of scale. Why concave function? It means what? If I can produce 10, and the unit cost would be more expensive than the unit cost if I could produce 100. Would that make sense? Why? Well, if you produce the same item, of course, if you can put that into massive production, usually the unit cost will go down. So that's what it means for the concave function reflecting the scaling of from the economy. And in that case, would the problem be easier? Yes? Why? How do you know? This only says what? The cost for each stage. You can save by producing more in terms of the unit cost. But still, the overall objective function is about the multiple stages. And for instance, if you take the sum, let's say if you take the sum of two concave functions, do you get concave function? If you take the sum of two convex functions, your function is still convex? You think so? And what about concave function? If you believe for convex it is true, then why you think for so long that for concave function it will be different?
I think it will be sum of two convex functions.
Okay, so if you believe the sum of two convex functions is also convex, then why the sum of two concave functions you think it may not be concave?
It will be. I was just thinking if the first one is correct.
Neither of them are.
Okay, so I guess if you have one function which is convex, I just denote by f1, and then another function is f2, okay? And then the sum between this, is it still a convex function? And how do you know? Well, a convex function means what? Well, let's think about strictly convex means what? For this function, you pick any 2 points, what? You make connection, then this line is above that, right? Yes? And then what? If you have another function, you would have the same thing, right? Which means what? If you think about this is f1, and then let's think about just alpha x1 plus 1 minus alpha x2. That's my y, okay? And then this alpha is some value within 0 and 1, okay? And what about this f1 of y? It's where? It's somewhere here, right? It should be what? Less than y is somewhere here, right? If this is x1, this is x2, this is y, right? And then this is f of y, and then this is what? Alpha f of x1 plus 1 minus alpha f1 of x2, right? And this is also true for what? For f2. Okay, and then what about f1 plus f2? For f2, I can write the same thing, right? Do you agree? Yes? And what about f1 plus f2? You take the sum of, on the left-hand side, you take the sum of right-hand side. So what? So it should satisfy this strict inequality. Of course, for convex, I should write less than or equal to, right? And then, of course, you can take f1 plus f2, of course, of y should be less than or equal to whatever you write alpha of f1 plus f2 of x1, and then plus 1 minus alpha, and then still f1 plus f2 of x2. So overall, this the sum of two convex functions is convex. Okay, so for those of you who are not very familiar with this, then probably you need to remember that's a nice property of convex function. And because of that, then of course, with that assumption, then what? In the multiple stages, the property you should not expect that to change, right? And would that simplify the problem? Basically, what does this mean when you think about this nonlinear programming problem? If you make such assumption, then what? Then there's a hope that you can find unique global minimal. Okay, so for this problem, is there any way we can simplify the calculation for production and inventory problem? Because now we are talking about a discrete optimization problem. In this case, basically, I'm asking you to think about whether dynamic programming can be applied to the problem. And what's the objective function in this case? That's here. Okay, so what does that mean? You have T stages, right? Each stage you have what? The cost of producing X products, right? And then what? And the cost of what? Storing I products. Why you need to store that? Because what? Basically, how the storage is related is based on like what? If the demand at stage T is dt, you produce xt, your previous inventory is it minus 1, then what? Then basically, if you meet the demand and you still have some remaining part, then that's what you have, right, in the storage, right? And the constraint, of course, is that the inventory cannot be negative, right? Can be 0 or what? Up to some upper limit. And also the production cannot be negative, can be what? From 0 to some also capacity, okay? So think about the constraints are all linear. The objective function can be linear or nonlinear, can be, for instance, concave. But would that really help you to solve the problem? I would say not really if you consider this x of t can only take integer value. The point is that this optimization problem is in general hard to work with, but it has some nice structure. It involved with multiple stages, right? And then what? This constraint tells you what? The inventory only depends on what? How much you produce at this stage and what? How much demand you have, and then the previous cost, right? Oh, sorry. Oh, I think someone should remind me on switching to this. Okay. So maybe let's look at this objective function again and think about this is the cost to produce what? X product at stage T. And this is the requirement of store some extra product at stage T, where the demand is D of T, and both the inventory and your production have to be what? Non-negative, and usually takes integer value. It has upper limit on your production and storage inventory capacity. So because the decision variable is what? It's not continuous, then basically the problem becomes harder. So any idea how in general we solve this problem? If, like what we explained, if this C and H are linear functions, then we are looking into what? So-called integer programming. Linear function, then it's like mixed linear integer programming. If they are nonlinear function, then what? Then basically it's considered a very difficult problem to begin with. And last time we also talked about some approximate techniques. For instance, assuming these decision variables can be what? Can be continuous without integer constraint, and then what? And then you solve the problem, and maybe it is not a good idea that you just round to the nearest integer. In general, what you need to do is apply so-called branch and bound technique, that when you convert to the integer of the decision variable at each stage, you try to compute the upper lower limit so that whenever it bounds within the integer value, you don't need to branch further. On the other hand, this problem has a very nice structure that shows the overall objective function can be decomposed into what? Multiple stages, right? So can you sense that maybe we can apply what? Dynamic programming, but can we directly apply dynamic programming to this problem? Any idea?
I think so.
Yes.
For each day, we mark each stage.
How? So you decompose this into different stages, and then what? Stage 1, you do what? Basically, how do you really make sure that each stage you get the minimal? Yes, we can decompose this into different stages, but then what's the actual difficulty? From one stage to another, what would be the transition? How do you connect this to like shortest path problem, where we travel from New York City to Los Angeles? Because in that case, we are measuring distance from one city to another. And here, It's some cost function. Involved with what? How much you produce and what? The inventory you need to maintain. Any idea, any suggestion to this? Well, this is a really good example that you see that even though you understand the basic idea of dynamic programming, but in real engineering optimization problem, it's not so easy to apply the technique unless what? You really understand very well about the key assumptions you need to make and how to decompose the problem into what? Multiple stages where at stage T, you only rely on what you calculated on the cost from stage T plus 1, and then what? And then the state that you go from T plus 1 to stage T. And here, I guess, if you can answer this question, then you probably know how to handle. What is the state in your dynamic programming formulation? Because in shortest paths, the state is what? Different cities, right? And here, what you model as a state? I'm sorry? Xi, the quantity you produce, right?
Oh, yeah.
Okay.
And also the quantity that you have stored. Is that also part of your state?
Okay, the quantity that you stored is also part of your state, okay? And how large the size of your state in this case?
You mean how many states are
Yes, like how many cities, and in this case, how many items?
For each stage, you have B times C states that you could be in.
You have B multiply C.
At most, yeah.
Possible states. Very good.
Yeah.
And then what? After that, you can what? You can find from one state to the other, and some transition may not be possible, but basically you are talking about B multiply C possible states, right? Very good. And then for each stage, you have what? The cumulative cost from the previous one and then the transition, right? Based on your objective function. Okay, so this problem, in fact, can be addressed by dynamic programming formulation where the cost can be some general function. And what we need to assume is that the units of demand, production, and inventory are integers, which, of course, is not very unrealistic in many practical situations. But if we don't use dynamic programming, then what? Enumerating all the possible ways to do the production and inventory will be computationally very expensive. And this technique will be efficient if the magnitude of the numbers involved is not too large, meaning what? B and C cannot be very large numbers, okay? And, oops. So we must identify stages. In this case, that's clear. And then what? States. We have what? The inventory level and decisions, which is like the production quantity we are going to make. And we need to find some recursion, from stage T to the minimum cost start from stage T to to the end. Okay, but how basically we can build our recursion? Well, if we know this function C for production cost, if we know this H for the inventory cost, then the constraint basically is our relation from the previous stage to the next one, right? So naturally, you can think about this C is the cost to produce X, right? This H is you have I in the inventory, and then you produce X, and then you subtract out the demand at stage T. Then that's basically how you get this for for the inventory. Of course, if you think about intuitively, you want the inventory level to be close to 0 in most of the time. And of course, your cost should start from the final stage, which is like this. And then you will always try to end up with 0 inventory so that the final period you have the production that meets that meets your final demand. Does that make sense? At the final stage, you only produce X that meets the demand because you have I in the inventory. Make sense? And what's next? Then you need to know the previous stage, right? The demand at not capital T, but T minus 1, and then And then determine what if demand minus the inventory is smaller than 0. You mean that's not possible? That could happen, right? Then what? Well, you cannot meet the demand, yes. But what's the implication of that? That means what? Either your production level is not enough or your inventory level is not enough, which means you should not consider such a configuration in your dynamic programming, right? And what if the demand minus the inventory is greater than the production capacity? I guess same thing, right? Because that's not a feasible configuration, then we can eliminate such a transition in the state. Okay, so what kind of cost can we calculate from this? We want to make sure that we have sufficient storage capacity, which means if previously you have inventory I, and then you produce X, and the demand is D, T at stage T, then what? This is what? Like your new inventory level, right? You want it to be below what? The inventory capacity B in such a case. And that also implicitly limit what? How much you can produce, this X. So we have to make sure that we deliver on time, which means what you have, you produce X, and then with the inventory, and then what? This is the demand at time T. This is always non-negative, meaning that you always produce enough to deliver so that you try to maintain the inventory level. So you'll see this X will be bounded by this upper and lower limit, meaning that the difference between the demand and the previous inventory will be the lower limit. And the upper limit will be what? The inventory capacity plus the difference between the demand and the previous inventory you have. Make sense? So it's like you can only produce less than B extra product just to save for future demand. If the future demand is beyond your inventory capacity, then no way you can meet that demand. On the other hand, overall, you have what? The previous cost plus what? The cost of producing X and the cost of putting this into the inventory at a different stage. Okay, so this becomes the recursion that you can use to find what? The minimum within what? Within X taking value from where? From 0 up to what level? Either the minimum of either what? The capacity you can produce, C, or what? Or the difference between what? Between what you produce in extra and the inventory capacity, meaning that you don't want to produce more so that it's beyond the inventory capacity. And also you cannot exceed the production capacity. So overall, I would say the number of states you can enumerate cannot exceed C, right? And Rustin just mentioned that in general, the number of states you want to explore is like what? B multiplied C? At most. But in fact, it can be what? Much less than much fewer than the number of states that we put into that configuration. Okay, so simple example, let's say we consider 4 periods and the demand is 1, 4, 2, 3. Okay? And inventory holding cost is 50 cents per unit. And production cost is fixed setup of $3 cost plus variable cost of $1 per unit. So how do we meet this? Of course, we need to also say about the capacity constraint. Let's say C is 5 units and inventory is 4 units. Okay? So intuitively, how do you want to schedule this? You go forward or you go backward. For instance, if you think about you don't want to put any inventory, then what do you do?
Just produce the same with demand.
Produce the same as the demand, then what? You don't have any holding cost. Is that good?
$3.
Okay, so what would be a better strategy?
Intuitively, just produce twice, each time produce.
You produce more, and then what? And also put that into inventory, and then what? Intuitively, your first time you produce five units, and then what? To meet the demand, and then what? And then at stage 3, you also produce 5. That's what you want to do. Okay, that's a very educated guess because you saw the production capacity is 5, and then inventory capacity is 4, then the demand is 1, so that actually touch both production and inventory capacity constraints. And the reason of doing that is what? The inventory holding cost is cheaper than the fixed setup cost when you do the production at each stage. Okay, if you think about dynamic programming formulation for this problem, you have 4 stages, and then the last stage is 3, and the cost is like this. Last stage, of course, you want it to be what? You want to meet that exactly. And for inventory is 0, that means what? You don't put any inventory in. Then you have this cost. If you put 1, then what? If you have 1 in the inventory, in fact, you can save, right? And then if you have 2 in the inventory, you can save. If you have 3, then what? Then of course, the last stage you don't have anything. Then of course, that you see intuitively it's good to put something into the inventory. But then of course, the next stage will have some problem. But what if you have 4 in the inventory? What do you think? Is that good?
Make too many trees.
Okay, so that doesn't really make some sense, right? So do we need to consider that? No, okay, good. So should we put that into 0? Make it a very large number. Well, why?
Or just not that case.
I think if we make it 0, would that be good? No, why? Because it doesn't distinguish between this configuration and this one, right? But if you put a very large number, or you just delete this, which way do you prefer to do?
I'd rather delete it.
You'd rather delete it? Okay. Any other opinions? Do we need, basically, is there any reason we want to keep this branch? Well, in this problem, I guess no. Because what? There's no reward for producing more because it's simple, just additive cost. Okay, so now you think about next stage. The cost at the beginning of stage t equals to 3, you have a complicated situation where you have your previous cost, that's what we calculated before, and then what? The cost linking to that. And from stage 4 to stage 3, you need to consider what? The previous cost and the inventory and the production at stage 3, right? So what do? You just keep calculating this, like what we did, and then eventually get to what? The beginning stage. And after some calculation, I guess you will end up with what Mr. Gang Liu just mentioned, that it would be nice to what? Compare the first stage on what basically you need to do for the production. So the best solution would involve is what? Try to produce more at the beginning stage and put that into inventory to meet the demand in this example. And this basically says something about how dynamic programming may work, but with a problem that involves different stages. But let's think about if we are not doing dynamic programming. Let's say if we just try to be greedy somehow. Let's say if we just say we want to produce as much as we can, would that work? If we want to produce as much as we can to flow the event to basically, how should I put it? To fill up the inventory, would that work? Why not? If the demand is lower, the okay. Then let's say if I just fill in the inventory and then reduce up to a level that meet the demand, would that work? I first just try to produce up to my capacity limit so that I also can fill up the inventory. And then I try to, whenever I see the demand is smaller, I just reduce one item at a time until it meets the demand exactly. Would that work? Well, I first just find a solution that just try to produce as much as I can to fill in the inventory. And then I say, because like what Rustin said, sometimes that's doing too much because later I don't have such a huge demand. Then I reduce one item at a time until I fit the demand. Would that work? Well, let's take a short break, and then maybe if you guys want to have some discussion, that's fine. And then maybe after 5 to 10 minutes, we will revisit this.
I found some mistakes. May I fix them tonight and send them to you?
Okay.
Like, well, the main mistake I found here is like this should be k plus 1.
Okay, would that affect your results in the report?
I'm not sure how significantly affect. I also forgot there's the last iteration for Fibonacci that it's sort of funny that I have to do the minus epsilon thing.
Okay, then maybe you don't have to submit now. I mean, just send me a revised version of your report, yeah, with the modification of the code.
Okay.
Okay.
I also have to want to ask you about this because from what I understand from your email, the Fibonacci iterations I should have did is 3. But I found 5 from this. I mean, this is basically in our book 1 plus 2 epsilon over. They had 0.3 over 2, so that's why they got 0.15. In this case, it's 0.23.
Okay.
And I found out this number is 9.56 something. And the only thing that's greater than that is F6, which is 13. So I know my iterations is 5.
Okay.
And I never examined the difference between them since then. I just run it 5 iterations.
Well, I think in your table, basically, I don't know. I think you probably didn't provide here. I think you sent me a table on the.
There's a table here as well.
On the required. Yeah, that's what I'm looking at.
Yes.
Yeah, and then I think I have these raw values on Fibonacci slightly different from yours. I'm not sure if let me see if I have some. Yeah, I think I probably agree with what Rustin did on this. This is its raw value starting from 0.4 and then stops here.
Well, How do I calculate how many iterations I'm supposed to do?
Well, basically, let me see.
Because I've been using, I have.
Do you know where his office is?
I've been using this formula here to determine how many iterations I should make.
Well, I think you have this epsilon equals to what?
0.05.
0.05?
Yeah, in this case here was 0.05.
Okay, and let's see. And then you're using...
And this here should be 0.115 because this is 0.3 is the uncertainty.
The range, yeah.
Over 2. So.
But what I'm saying is, I think you have some requirement on the uncertainty range, do you?
It says epsilon's 0.05. It says repeat part B using the Fibonacci method with epsilon 0.05.
0.05, okay.
For part B, the uncertainty was 0.23.
0.23, okay. Oh, I see. So you did a few steps more. Okay, that's fine.
I actually have a method that calculates how many steps I'm supposed to do.
Okay, that's fine. But what I'm saying is, let's see if the actual range is, because it seems that this actual range and the value evaluate are different. That's why I need to see how you calculate the interval.
This one is fine, this first one, but I think for the next ones, I used the previous values of rho, which messed me up.
Okay.
But for my rows, I calculated some of my rows by hand.
Okay.
To show that I think my row values are correct. I just applied them incorrectly.
Well, your row values are different from what I got, so that's...
Well, row values depend on how many iterations you have.
Yeah, but I see. But in this case, you said that you
5 iterations.
You need 5 iterations. Okay.
Yes. So I have 5 rows. So that's why my row values are different.
Okay, that's fine. Yeah, I think like I said, that's okay. But provided like what you did, you give me some explanation like this. That's good enough.
Okay.
Yeah.
Okay.
Okay, so maybe just send me a revised version of your report.
Okay.
I mean, I don't. That's why I say that I calculate slightly different from yours. I'm not saying that your project doesn't work. So I mean, you can stay with your calculation. I just want to take a look and to see that the assumptions might be different from what I did or what Dresden did. So.
Okay. Thank you, Doctor.
No problem. Yeah.
That problem with the airplanes.
Okay.
And the destinations that we have to collect these little stars on the ground.
Yeah.
How do you solve that?
How do in general? What do you mean in general?
Like what approach would I use to solve a problem of that type?
Well, in general, you enumerate all the possible configurations and.
But I can't even if you have. I was thinking about it. If you have 2 planes.
Okay.
3 stars.
Okay.
Even enumerating that is complicated.
Well, what do you mean by complicated? I mean it's combinatorial in nature.
It's hugely combinatorial. It's not just simple because you could have one plane getting all 3 of them.
Well, that's not good, right?
But it's still a possibility.
It's feasible, yeah.
Because I was trying to think in this little diagram, I think the optimal solution is for one plane to get these 2. And for this plane to go straight to the
could be. Yeah, that could be. That could be a good solution.
It's a little bit quicker than doing from here to here and doing that.
Yeah, could be.
But I don't know how an algorithm would differentiate these 2 cases.
Well, no, you have to enumerate. And sometimes because of the constraints that make the enumeration even more complicated because most of them will not be feasible.
Right. But,
and checking feasibility sometimes is considered very inefficient if you don't have a good way to avoid that.
Right. But the only solutions I can think of are kind of like greedy or heuristic things that might not find an optimal, but should find something that's kind of all right, I suppose, Well,
how do you know it is all right? That's a very interesting question to ask. Yeah, so later we are going to see that when we say suboptimal, we mean we know. We mean really we know it's suboptimal, meaning that it's close. Yeah.
something that's not the worst is better than the worst, obviously, right?
Yeah.
So that's what I mean by all right. It's
Yeah.
not the worst solution.
And if I have time, maybe I can cover a little bit on the approximate algorithm to solve this. Like sometimes you can say, I cannot guarantee you I will success most of the time, but the chance that if you apply this, that I can get a reasonable solution, the chance is high. Meaning that sometimes I say I'm 10% close to the optimal, that's not acceptable. But sometimes I may say I'm 90% close, then I will stop. But how long does it run?
Right.
Depends on a lot of things. Still, it's approximate, meaning that I'm not pursuing to say I have efficient algorithm to find the optimal one. But however, it is useful for some problem like this. Yeah.
Right. Like I was thinking we had a problem in Dr. Zhu's class that was stepwise model selection.
So that okay.
Like you have a response variable and you have some regressors.
Okay.
And you want to find some subset of these regressors in
Yeah.
order to predict this.
Yeah, but you don't want to do
But you don't want to
enumeration.
enumerate them, right?
Yeah.
So you pick.
Well, you can do
some-
greedy approach, like when you say stepwise, like step up or step down. That means you pick one at a time. Yeah.
Right. So you do something of that sort. But one of the problems is that if you don't start in a good spot, you might kind of be stuck there. Like you have to have an initial.
Wow.
Let's say like you want a model of size 4, for example.
Yeah.
Then you use a model of size 4, and you kind of like.
Well, in general, if your criterion doesn't have any structure, then no way you can be efficient. If you
Right.
And sometimes you can change your objective function, meaning that you can put some extra term to make it easier, and then relax later.
Right.
And that's what a lot of people do. So.
I'm just trying to think of ways to do this problem.
Yeah. It's a hard one, and if you want, of course, you can propose to address this problem in your term project.
I don't even know how to do it though, other than like I can do it exhaustively, certainly. It might take a while. I can do it, and then I can do a greedy, not guaranteed in any way, shape, or form to find anything.
But you can do a greedy, not so greedy, but still a greedy type of approach with guaranteed performance measure on how close you are to the optimal one. And that's what we covered a little bit on the so-called mixed integer linear programming. And that can be extended to this.
I don't understand, because these solutions are not integers in the sense that they're rankable.
Integer is in terms of like how you really cover this.
No, even the order that you approach these in, there's no guarantee that star 2 is bigger than star 1.
Yeah.
Like they're classes, they're not like numbers, they're not sortable.
Yeah. Well, I guess first you need to think a little bit what would be the best way to cast this into your own optimization problem. Okay. And then maybe what approach that might work somehow. And I believe this is a very important problem. I mean,
it's hard.
Yeah, and I would say for large scale problem like this is a difficult one. But a lot of engineering optimization problems are like that. So we cannot say, well, there's no way we can address that. We have to find some acceptable algorithm that at least to give it a try. And that's why I just mentioned there are some commercial packages that help you to basically to pick some toolbox to begin with. And there's no guarantee that will work, but still it's like at least it builds some baseline for you to explore further. Okay, so if you think about this production and inventory problem, it has some analogy to so-called network flow type of problem. I think maybe last time Sire mentioned that he's interested in knowing more about network flow problem. And this is like a simplified version if you think about why. For instance, if you think about this, it's like what? You're putting production line, your demand is like what? something like at each stage, you can say, I take how many customers being in the service, right? And then you have the flow of putting in more customers into this queue, and then what? And then the queue eventually will be consumed by the server. So basically, you can think about this like some kind of queuing system goes like this network flow. So this is like just a single line of flow. In general, network flow means what? You have some topology or the direct arc connecting from one server to another. Then it will become more complicated. In this case, I'm trying to give you some idea about so-called network representation of the problem. And in this case, of course, a node means what? A node means a particular state at a particular stage you're talking about, right? And the arc connecting the node are what? The decisions on how you're going to do the problem. And the arc from stage T and then the node I indicate what? The inventory correspond to some kind of decision. You want to produce X items, then from stage Ti, you get T plus 1, I plus X minus dt, and dt is the demand. The demand, you know ahead of time. That's for your planning. And the cost for this arc is this C. That's the cost of producing X and the cost of getting the resulting inventory. So based on this structure, you can write what? Some kind of a directed graph connecting what? Nodes at different stages with the cost. And then basically you can have a very nice representation for what? Pushing the overall cost to the minimum. And that can be interpreted as having some kind of network with what? Some flow coming into it. And another similar argument you can say is, for instance, if you have a complicated network, how much flow you can put from one source to the destination that actually meets this network capacity at different arcs. That's also optimization problem, indiscrete in nature. How to solve that? Of course, you can also apply so-called dynamic programming idea to do that. And there's another type of problem which you can think about that's also important in discrete optimization. So Lippy probably heard about that before. This is what?
I know this problem.
Okay. Okay, so the problem in a simple example is like this. A company is considering 4 possible investments. And if you think about, for instance, investment 1 will give you a net present value of 16K and requires a cash outflow of 5K. And investment 2 will have this net present value of 22K, require cash flow of 7K. Which one is better? No idea. Why? I'm sorry? Between NPV and the cash flow is larger. Why that's good?
Because she says the ratio of these numbers.
Because the number of units in cash flow, you got more back.
Okay, at least that's in layman's term how you buy stocks, I guess. Okay, but in general we don't know. So, but this is assuming that you have such a way to measure the investment. Then you have this 1, 2, and 3. I'm sorry.
What do you mean by cash outflow?
You put more money into this investigation.
Investment.
want to buy a stock, you put type 1 stock, you just put $10. Type 2, you put $15. But if you earn something from type 1 stock, maybe $10 you can get $5 back, but 15 you only can get $3 back.
Okay, I'll go.
Well, I would say this is just some simple example about when you do some investment. Let's say you have 14K budget, and let's assume that you cannot put everything to investment 1. Why? Because
Want to diversify your assets?
well, we are not getting into the actual real investment. It's just because of the size of the investment. You have to make it like like integer amount of certain, like 5K or whatever. And in general, because of the integer constraint on each investment, then you will think about, I want to maximize, of course, the amount of this investment on first, second, third, or fourth, subject to what? Like the integer constraints on these 4 different assets. And of course, by looking at this, you may see that for each unit, like what Nan just mentioned, the actual value you have depends on like the ratio between you cash outflow and the NPV and the cash outflow. So from this, it seems that investment 1 seems to be a viable choice to consider because it has has the highest value, and of course they are all maybe about 3 something. But then what will happen is that if you think about of the integer constraint, then what will happen is that if you put integer quantity on this, then what will happen? Then you have to pick some other ones, right? And in general, I'm trying to say this so-called knapsack problem is about some planning of things that you try to pack into your bag or whatever. Like you're planning for some hike, and then you consider taking 4 items on your trip. And then you may say item 1 gave you some benefit of 16, but weigh 5 pounds. Well, that's, of course, easier to understand than the investment analogy. But basically, this net present value is about this kind of benefit. And then if you think about this cash outflow, it's something like you invest something, it's like it has some weight you got to carry. And then you can say item 2 is like this. It has benefit 22, weighs 7 pounds. Item 3 and 4 are like this. And then you value them like you want to what? Maximize your benefit, but you cannot carry more than 14 pounds. Then what item you need to put in? Okay? And that's the type of problem called the knapsack problem. And this is very important for some kind of resource allocation. When you do some manufacturing and some other things, when you do scheduling, you encounter such kind of problem a lot. But how do you really solve such a problem? In general, by enumeration, I would say. Well, by what? By enumerate all the possible ways to pack into your pack, right? Because if the problem is not of large size, in general, that's the easiest way to begin with. Yes?
So it's in the NP complete class?
This problem, what do you think?
I think so.
It's in NP complete class. Well, some problem, some knapsack problem can be cast into NP complete class, but
I think one of the either discrete or continuous. There are two versions of knapsack problem, and one of them is NP, but one of them is not.
one of them is not. One of them is.
Yes.
You mean the continuous version of what?
Continuous version of knapsack problem. For example, here in this case, you have weights, and you also have weights and the price of that item. Suppose, for example, in computer science, they formulate it as there is a thief and he wants to collect lots of items.
Okay. Okay.
So he wants to map.
Okay, so I see. So you're saying that, for instance, you can pick not a single item Y, you can pick maybe half of that or a fraction of the item, and then still you have fractional value on that.
So there is another version of.
Okay, so which one is harder? But in your intuition, fractional one or integer one? Integer one should be harder, right? Intuitively, why?
Fractional one
You can interpret that as continuous objective function and constraints are basically either linear or nonlinear, but the decision variable is in continuous domain, which means you have some tools to work with. But the integer constraint is usually much harder because in general, you can only relax the integer constraint, but you cannot what? You cannot say I don't have such a you can only say I don't have such a constraint. I try to solve a relatively easier problem without a constraint, but you cannot say the opposite. If with such a constraint, then what? Then essentially, in some cases, if you don't enumerate, there's no way you can guarantee you get the optimal solution. But still, you can try the idea of dynamic programming. And this is just the version that we talked about. And then you can say, in general, you want to consider n assets with some NPV value, RNDN, and also you have to take the portion DN for $1,000 amount in the investment, and you only want to invest integer multiple for $1,000. And then, for instance, you can have these values, like you don't invest or you invest some integer value. And then the problem will become some kind of integer programming. And this, for instance, when a equals to 3 and b equals to 6, then you have some constraints like this. And in general, we know this is what? Like NP complete problem, but what's the implication of that? In layman's term, it means what? In general, in order to find the optimal solution, it seems that there's no better way than enumerating all the feasible solutions and then pick the best. And you cannot systematically eliminate some solutions during this search to make it more efficient. But we don't know if there's any stochastic way we can achieve that. Meaning that, for instance, there's a hope that by randomly picking some solution at the intermediate stage, we may be very lucky most of the time that we get to the best solution very quickly. That no one knows, but still it's considered a very important technique to do optimization, which later I hope next time I'm going to talk a little bit when we get into so-called global optimization technique. And if you think about, a general formulation would be to maximize the overall benefit subject to some integer constraint on the individual portion. So this problem is difficult to solve, but still we can formulate this as dynamic programming. And in this case, you can think about stages means what? Like, well, like each category you pick for the investment, right? And then states means what? Somehow your available budget, even though this number of states can be huge, but still, if you take integer values, like in this example, it's from 0 up to 6 in your budget. And the decisions are investment amount on each asset that you're going to do. And of course, you can try to solve the recursion for maximum return from individual from the investment categories in these 3 different cases. In this example, we are looking for what? The final stage, right, on this. And if you think about maximize the benefit for stage 3, that means what? If you don't put that into asset 3, you get 0, right? Otherwise, you can what? Get something from this investment. And you will always invest all your remaining budget in category 3. Why? Because what? Like what Nan just mentioned, if the marginal value is larger than others, then you want to do that. And this will be the workflow for different stages that you try to calculate the individual cost for picking this asset. So let's go back to the original problem formulation. So if you think about this involves different stages, and each stage you have budget constraint. And that means you can confine your possible states in each stage. That's important when you do dynamic programming. I think the most important requirement for dynamic programming to work for complicated problem is what? Is that you have such a way to control what? The number of states in each stage that you're going to find either the maximum or minimum among different parses going through those stages. So if you think about this problem, then by looking into small scale size problem, then you can actually return from the investment in category 2 and 3 whenever you have some extra. So that's how you look into this problem. And of course, those subproblems are a little bit harder because what? Because of the integer constraint that enforce the intermediate stages, meaning that, for instance, you can say I need to compare between invest on the first one or the second one, and so on and so forth. And sometimes when you invest on one asset, you cannot invest on the other, then the maximum will be small. If you can, then the maximum will be larger in the second stage. So by looking into all these combinations, eventually you will get to the best solution for this problem. And why we say still the problem is NP hard, even though you see dynamic programming can solve the problem. I think the answer lies in how we view the problem, right? Here we made some assumptions like what? The number of states will not be very large, and the number of stages will also not be very large. But in general, these will define the size of your problem. And dynamic programming cannot scale very well when you have the number of states increases exponentially, let's say. And then what? Also, it will multiply when you think about multiple stages. Then, in general, solving dynamic programming will become computationally infeasible in that case. And of course, the most important characterization on this is that we try to put the problem into some network representation where we identify nodes and what? And the arcs. Usually the arcs are related to the decision, and nodes are the stage and state combinations. And then we want to know from some node I where you have what? You have this Y as you benefit toward corresponding to a decision X in another node from the next stage. And then you can return basically the revenue if you put D from your investment to this asset in stage I. So this is some objective function with respect to decision variable that takes integer values. And this is, in general, the constraints also that correspond to some capacity limit for each stage. In general, you can say resource allocation can be viewed like this. For each stage, you need to determine how much resource you allocate to each particular production line or whatever. And then you get some revenue for doing that, but also you have some constraint on the total resource and also individual constraint on each resource, how much you can produce. And also there's an integrality constraint like this, meaning that you can only allocate the resource 1 unit at a time. Like there's a granularity condition. You cannot put a fractional resource to the production line. And in general, this kind of problem can be formulated by dynamic programming because what? The cost can be decomposed into what? The sum of multiple stages. What if the cost, the objective function is the product of the multiple stages? Can it be a dynamic programming problem? No. But in fact, it can be converted easily to a dynamic programming problem because what? If you take the log of your objective function, then it can become what? Just the sum of the individual stages. And this is important because product sometimes, when you have independent observations, for instance, by taking the likelihood function, which is the product of the individual likelihood function for each observation, then maximizing the likelihood function will be what? Like the product of each individual likelihood. And then in general, still you can what? You can decompose that into multiple stages. That's what I'm trying to say. Because this objective function is decomposable. However, sometimes the constraints may not be that nice, because also the state that you are going to deal with may become very large. Then the problem, in fact, is difficult. There's another possible application where, for instance, we can say it's about equipment replacement. A company faces the problem how long a machine should be utilized before it has to be traded for a new one. And for instance, you may say a new machine costs $1,000 and has a useful life of 3 years. And maintaining a machine during its first 3 years costs, like first year $60, and second year $80, and third year $120. And a machine is traded, and then it still has a salvage value. For the first year is $800, and second year $600, and third year $500. After first 3 years, then you basically need to have a plan. For instance, you are currently have a Y-year-old machine, and what would be a policy that you can minimize the total net cost over the next 5 years? And this could also be considered as a dynamic programming problem. Or maybe you can say optimization problem that can be solved by dynamic programming. The reason is what? It has these multi-stages in the decision. And each year, in fact, the decision is fairly easy, right? You have what? 2 choices, right? One is keep it or you trade it. Okay, so in 0, 1 through 5 years, you have this problem where you have time and stages and also the age of the machine, right? And then your decision is either keep it or trade in. And you have some kind of recursion on the minimum net cost after a certain period. And clearly, you want to find a policy that's basically work for the age of the machine. And you may say, well, I want to salvage the machine at the end of year 5. And the net cost after period 5 is this. And then what happens in the previous time? Well, you have one decision to keep it or another decision to trade in, and then you have the value associated with that. And then if you keep it, what? You have maintenance cost, and then what? You have the investment money. Otherwise, you trade in, you lose this. So at the end of the whole period, you must decide whether to keep it or trade in. And next, if you trade in earlier, then what will happen? Because in fact, it's a little bit asymmetrical, right? If you keep it, then you have some value to calculate. Otherwise, you may say, I already traded in first year, then you don't have that branch. So you have some kind of recursion that branches to 0 and 1, but they are somehow asymmetrical. If you think about, at year 3, you must trade in when you have this kind of recursion, right? If you do have a choice, that means you can trade in early before that. And you can always think about any problem you want to work on the dynamic programming formulation. You need to determine what? The state and the stages, right? and then your decision to connect from one stage to the next stage. And in this case, you may say, well, if the maintenance doesn't really add any value, then basically if the maintenance cost is too high, then what? The trade, then the difference between the net value and the maintenance, then I should trade in, right? If I can still, the marginal cost between what I have and what I, in this particular example, what would be your solution? Let's go back to this policy. So what do you do? Yes?
Okay. What I'm saying is, if after a year you trade the machine,
Yeah.
it's like you're losing $260.
Okay.
For 1,000.
Okay.
Trade it in for a value of 800.
So you don't want to do that, right? Oh,
yeah, but if you trade it in after the second year, you will lose a value of $460.
Okay.
Which is better than trading in with the first year, because you didn't have to. If you were trading in year by after year, you will lose 520 over 2 years.
Okay. So at the year 2, if you don't trade in, of course you have the machine, but in year 3 you will have some problem, because at that time when you want to trade in, the net difference is $100, right? That's what you're trying to say. And then the maintenance is $120. And because of that, you go backwards and thinking, no, I should trade in earlier, right? Okay. And dynamic programming just go like this. You say, well, when should I trade? And because each stage is like, if you don't trade, it's because what? You are already adjusted the net difference between the original value and the trade-in value and versus the maintenance cost. And you think, I probably can make profit to cover the maintenance because of the depreciation value is not that high. On the other hand, when the maintenance cost increases and your trade-in value cannot cover that, then before that, you should trade in, okay? And of course, this works in general when you have a way to write the problem into an important structure. That's like, this is an important tool for discrete optimization. And I would like everyone to remember that the optimization problem involves a sequence of decisions. It can be solved sequentially by finding the state that contains part of the optimal sequence. Meaning that in general, the complexity depends on what? The number of states in each stage. But doesn't depend on the real scale of the problem. You don't really enumerate. You just enumerate within what? The number of states in the previous stage with the associated cost, and the cost to go from there to your current state. So it's just the transition from the one state in the previous stage to the current state. And that you need to evaluate which one is better. And also that the optimal solution should always contain part of that so that you don't lose any optimality condition in the solution. And in fact, this technique has many names in different engineering applications. So for instance, Bryce is working in communications, underwater communications. And in communication, an important technique is how you decode the transmitted message through some unreliable channel. And in order to do that, there's so-called maximum likelihood sequence decoding algorithm proposed by Andrew Viterbi, and some people call Viterbi algorithm. That's basically one version of doing dynamic programming, which is very efficient. And also in so-called network flow or shortest path, but in general, you can say if you have a directed acyclic graph, you want to find from one source to a destination, what would be the minimum total cost to go from location A to location B in such a graph? Then you have so-called dexterous algorithm to solve such a shortest network path or shortest flow problem. And that's also a specific version of dynamic programming. And also in some cases, Dijkstra algorithm can also be interpreted as one type of greedy algorithm, which means you can think about each arc, just try to find the best neighbor and propagate that. If everyone does that, in effect, it builds the optimal solution somehow. And later, we're going to also revisit that technique when we try to find a unified view on how to solve engineer optimization problem. And also, there's so-called the Bellman's algorithm for optimal control, where the control involves a sequence of input, and then in order to achieve certain goal. And the goal can be decomposed into some multi-stage objective function. And Bellman's equation basically characterizes the optimality condition for such a control problem, which actually is considered like the birth of dynamic programming, which becomes very popular in all engineering optimization area. People draw a lot of attention to that. So I guess that's pretty much about one important optimization tool for discrete multi-stage optimizations. Any questions? And because this is not really covered in the textbook, so I would like you to basically look into the slides. I may, at some point, provide maybe some simple example for you to practice in the homework assignment. But I do encourage for some of you who are working in your research topic related to optimization problem in discrete in nature, think about whether you can apply this technique to your problem and maybe have a project proposal on that. I think some students already send me email inquiries on what you may want to work on for the term project. And I would like to see that some of you, if you want to work on your own topic, please write to me like a 1 to 2 page description on the problem, especially not just the background information, but how you want to convert that into a mathematical optimization problem, and what technique you plan to explore to solve the problem that you're working on. It can be power system, can be communication, can be bioinformatics, can be estimation, tracking, or some other areas that you're working on. But don't send me some technical stuff saying that here's the background, please read about DNA sequencing and alignment algorithm and things that I have to dig into what you want to do. Provide a concise description on how the original engineering problem can be casted into a mathematical optimization problem and what you plan to do. And I hope that you can utilize what I covered in the class, but bear in mind, I may cover maybe some additional material depending on some individual interest. My plan is that next time, I may talk a little bit about global optimization technique, which is not that theoretical oriented, but still it's very appealing that in many engineering applications, you may want to engage in that technique. So if there's no further questions, that's it for tonight. And if you have not submitted your homework or computer assignment, then you can do that through email or maybe send a hard copy to me, to my office if you if you can come by before this weekend. Thank you. Yes.
So can our project be application based? For example, like I'm now working on networks.
Yeah.
Networks. So can I just make use of some existing algorithms which are based on optimization and make use of them in my work?
Yes,
Is
of
it
course.
possible? For example, now currently I'm working on non-negative matrix factorization, but
Okay.
there are many already well-known algorithms, but they optimize. There is some objective function, and they are based on finding the local optimal of some matrix differences of two matrices. So can I just make use of those existing algorithms and show the applications of that in my work?
Well, I would hope that, for instance, if it's some technique not covered in this course, maybe briefly explain a little bit how the algorithm works.
Yeah, sure.
And you said it's about non-negative matrix decomposition, factorization.
Yes.
But to me, it doesn't seem to be an optimization problem.
Oh, no, it is.
Well, if you, for instance, if you say, I want a matrix A equals to B multiplied C, where B and C have to be elements with non-negative, then that's not really an optimization problem. You need to convert, for instance, you say, well, maybe there are many different solutions for B and C. I want, for instance, maybe the minimum energy in terms of maybe the norm of B is minimal, then that's optimization problem. And then yeah, of course, you need to provide me some background. For instance, this is an interesting problem for your application because it involves some important bioinformatics problem. And then the key is to say, for instance, for this problem, I want to treat it as constraint optimization, and certain techniques are available, but then why, for instance, you pick a particular technique to address that?
Why non-negative matrix factorization?
No, I'm saying that, for instance, this is a constraint optimization problem.
Only with non-negative.
Yeah. And then, for instance, you say maybe this can be cast into so-called semi-definite programming. And then I can use so-called linear matrix inequality toolbox to attack that. And that's fine with me. But of course, it would be nice that you have your own contribution to this.
Yeah, but the contribution is on the bioinformatics part.
Yeah, but what I'm saying is, of course, that's your own research, but that's not of my interest to this course.
This is what I'm asking you, whether I can just make use of those.
Yeah, you can. That's good enough. But if you really want to do better, I would encourage you to write something like, yes, the existing method, for instance, is semi-definite programming. And then you may say it has some problem when working on maybe your bioinformatics application. On the other hand, you'll try some other method. Maybe you'll say, well, I prefer global type of method. I prefer other method. Because now we covered basically essentially a lot of techniques.
Yeah.
And then you need to make some decision on which one you pick. And it would be even nicer, for instance, if you propose some optimization technique. Like for your problem, because it has some specific structure, you try to do relaxation, maybe you try to solve not direct primal problem, you change that to dual problem. Things hopefully that's something related to some course material that you understand well, and then you basically apply the technique to your problem. That's even better. And of course, in that case, you may even have real publication out of that.
Sure. Okay, I will think about it. But in the worst case, at least I can make use of, I can just work on the application part of optimization.
Yeah, but what I'm saying is the focus of this term project, of course, would be how you explain the optimization technique. And the technique probably I don't have time to cover, but you understand and you try to basically explain how it works.
If I use any optimization technique which has not been explained in the class, then whenever I present or in my project report, I will.
Of course, it would be nice to think a little bit about whether there's any better alternative to solve the problem. Okay.
Thank you, Dr.
Sure.
The first one, when I find the points, how do I know which one is which one minimize with objective function? Even if I replace it, I don't know if it's a minimizer or a
Maximizer. Okay, I think you need to read the textbook on the second order condition. And another way you can do is to draw the level set for the objective function.
Just do it graphically?
Well, first you have some feeling about how the constraints may change the problem. For instance,
I could have done it graphically, but I thought the homework wanted us to use the Lagrangian,
Yeah, of course, I would hope that you do Lagrangian method and then take the gradient direction, set it to 0, and then take the second order derivative, get the Hessian matrix, and then basically check whether at your solution the Hessian, basically the Hessian matrix.
That's from chapter 8.
Yeah.
All right. Yeah.
Yeah, because that's important technique to really.
Yeah, I see it.
Yeah.
All right. Well.
Yeah. Well, if you want, you can maybe work on it and submit to me some later time if you want.
Well, yeah, I can do that.
Yeah.
And then in the same fashion, and then all of a sudden, there's a lot of you see if I go through Cincinnati, that there's a time to get to here. You know, if I go through Indianapolis, there's a time to get here. So Bloomington here is one of these ways, right? So it's easy.